We start this third unit with the concept of quantum mechanics. Again, this is a new type of physics dealing with modern physics. That's physics after about the year 1905. We spoke about relativity in the last set of videos, and now we move on to another branch of modern physics called quantum mechanics. And we introduced the concept of the quantum. What is a quantum? Well, it's an elementary amount associated with a quantized quantity. So that's the word quant is in there quite a bit, or the prefix quant. So a wonderful example of this is money, right? We often think of money as being, well, I can have any amount of money in my pocket or any amount of money in my bank account. Well, that's not true, right? You have to have some number of pennies in your bank account. So if you look at your bank statement, look at your savings, your checking account, or your 401k, or whatever you have, whatever accounts you have, when you add up all of those values, you have a set number of pennies that represents the amount of money you have, right? Your bank account never says you have, oh, I have $523.312847. No, you have some 0.38 cents or something like that. Now, of course, gas stations like to try to trick you in saying that they can actually charge you 0.9 of a penny, but in the end of the day, right, they round and you have to pay to the nearest penny. So that's a quantized quantity. Now, classical physics, the kinetic energy of a bus or the kinetic energy of a bullet can be any value. That was how we worked on it classically. It's not that a bullet had to go some integer number of meters per second, or a bullet had to go 1 meter per second, or 2, or 3, or 4, or some combination. It couldn't go half a meter per second, right? We think of classical physics as any value is allowed. When you actually look in the quantum realm, the realm of the very small, that continuous distribution of numbers doesn't exist anymore for some types of problems. For electrons bound into atoms, for instance, those electrons can only exist, we will learn, at very specific energy levels. For photons of light, when we talk about photons and the photoelectric effect in the next video, we'll learn that photons can only have very specific values. In fact, we'll talk about that a little bit later in this video. So quantum mechanics is the mechanics, or how the behavior exists of very, very small objects. Now, of course, quantum mechanics must become, as the objects get larger and larger, you go from atoms to molecules to sets of molecules and so on to gases. As the objects get larger and larger, or from a relativistic sense, as the materials get slower and slower away from the speed of light, the relativistic equations we learned and the quantum mechanics equations and discussions we will learn have to dovetail nicely into the classical physics realm. This is called the correspondence principle. The idea that quantum mechanics, while the behavior might be weird on very small scales, when you get up to the scales like this classroom, or the scales that you and I can see with the naked eye, classical physics dominates. Quantum mechanics must nicely dovetail into the classical equations we've already talked about. Relativity has to dovetail very nicely into the classical understanding of kinetic energy and momentum that we learned about last semester. So your book talks about a lot of different things in this chapter. So moving on, it talks about what's called blackbody radiation. One of the discoveries of the quantization of energy came about when a physicist, Planck, tried to figure out why the shape of a curve called the blackbody radiation curve was the way it was. So any object with a temperature above absolute zero. Absolute zero is 0 Kelvin. It's 273.15 Celsius, I believe, minus 451 Fahrenheit. I'm not actually exactly sure that number off the top of my head. Very, very, very cold, right? Classically, motion stops at absolute zero. If your object is above absolute zero, it gives off electromagnetic radiation. So you and I right now, because we are above absolute zero, we have a temperature above absolute zero, around 310 Kelvin or so, we give off electromagnetic radiation. That radiation isn't visible light. It's mostly infrared radiation. But if you keep on turning up the temperature of an object, like for example an electric range, You turn up the filament on an electric range, it gets hotter and hotter and begins to glow in the optical. That shape of the blackbody curve, and I'll show a blackbody curve up here on the right, that shape of that curve depends on the temperature the object is. All objects that have temperatures above absolute zero give off this curve of a similar shape. So the question becomes, why? Why does that shape exist? And Planck was trying to figure that out mathematically, trying to figure out why that particular curve existed. And what he ended up discovering was the only way he could make that curve work mathematically was by introducing a constant, which we will call Planck's constant. He says, okay, atoms exist as little oscillators that absorb and emit radiation. They absorb and emit radiation at discrete energy levels. Those discrete energy levels, the difference between those energy levels is given by the following equation. So the energy, for example, of light, of a photon of energy, is equal to this h, which is Planck's constant, times the frequency of light. H is a very small number, 6.626 times 10 to the minus 34 joule seconds. So Planck was the first to show that energy has to be some discrete quantity, some minimum quantity. So if you know the frequency of light that we're talking about, or if you know the wavelength and you know the speed of light, you can get the frequency. If you plug in the frequency of light, multiply it by Planck's constant, it tells you the minimum energy of light at that frequency. Light cannot have less energy than that. It can have more. You can have multiple photons, right? You have twice as energy, 3, 4, 5 times as energy. If you have twice as many photons, 3, 4, 5 times as many photons. But for a given frequency, there's a minimum energy associated with it. This really began the discussion of quantum mechanics and the quantization behavior of particles that are very, very, very small. This is very unlike the macroscopic world, the world that you and I live in. We don't see this quantization of energy. But at the atomic level, it exists. Your book then goes on, and I'll show an image here on the right of a spectrum, an atomic spectrum. So each atom, we will learn, an atom is a collection of electrons orbiting a set of protons. How many protons depends on the element. Those electrons are bound to the atom. They can only exist in specific energy states. An electron just can't be anywhere around the proton or the nucleus. It has to exist, depending on the element, at very specific energy states. Which means that when the electron moves closer to the nucleus or further away, it has to make very specific jumps, giving off very specific energies, photons of very specific energies. So we can use this to identify elements. Elements have what are called spectroscopic fingerprints or spectral fingerprints. All hydrogen gas gives off light at the same 4 visible wavelengths. All helium gas gives off light at the same set of visible wavelengths. All neon gas gives off light at the same set of visible wavelengths. And again, we'll show it up here on the right, what those colors are. So we can use this to identify specific elements. In fact, the element helium was first discovered spectroscopically on the sun before it was discovered on Earth. Helium is an inert gas on Earth, very difficult to find it react chemically with anything. So it was not found in the lab on Earth, but actually discovered in the solar spectrum first. And once the element was discovered in the solar spectrum, it was looked for on Earth and discovered.